All right. Okay. We're going to start now with essentially what is chapter 2 in the course book, lecture notes. And I already told you that essentially during the course we will have 3 different descriptions of light that we will work with. We had the photon description already. We have the electromagnetic wave description. And then, in a lack of better words, we have what I called the macroscopic description. Now, we will start with this one. It may be the one that you are most unfamiliar with since before, though you should have encountered it, for example, in a base course in astronomy that you have taken, inledning till the sterrekunde. And it is often what we use in astronomy to analyze light. In this, we see rays of light or bundles of light like this. As I mentioned, it is connected to the geometric optics limit also of light that you might have studied in a basic optics course as well. Now, this light, though, it spreads out as it goes here, you know. We can't analyze it perfectly. It's not perfectly collimated. So it spreads out like this in some angle here, which typically we call the solid angle. We will today define a quantity which we call the specific intensity, or just intensity in some literature, it's also called. Okay? A particular property with that is that it is, when you have such a bundle of light here, the specific intensity is the quantity that is constant along this ray, as long as we do not have any interactions with matter. And we'll come to that, what that means later. Huh? Now, I will also add that it is constant throughout the ray. That will be the case throughout the course here. But it's also, technically, one should add that as long as the frequency is also constant. Because if that changes, the frequency of light, this can also change, which is, for example, the case when you go to cosmological scales. Because of the expansion of the universe, the frequency of the photons change. So on the biggest of scales, we actually have something what we call redshift dimming of the specific intensity. That is, that the specific intensity also then decreases the further away we go. But as long as we are in the local universe, so to say, we do not have to really worry about that. But for those of you who are in the master's program, you will take galaxies and cosmology with me in the spring, and then we have to worry about that. The interaction with matter that can occur, that we will come to, in chapter 3, in fact, we can think about that in a very schematic and simple way as, okay, so we have light here now traveling. This is a bundle of light, a ray of light, if you will. And then perhaps we have some intervening materials, an atom, a molecule, something like that, dust, yeah? And then when the light ray hit the material, yeah, well, say it's an atom, the atom can absorb the light as one process. Then, of course, energy, delta E, is removed from this beam. Yeah, so then it's not constant anymore. Yeah. Another process that can happen is that, okay, say we had an atom, and that previously absorbed some light, so the atom was in an excited state. And then it de-excites. It goes back to a lower energy state of the atom, say. Then we can emit light as well. That's emission, such that if it's in this direction, then energy is added to this ray. And then we have essentially a third process, and that is scattering of light. And that's just what it sounds. Say you have a bundle, right, and you have an intervening particle here, perhaps an electron. Then it comes out, and then it can just scatter. And then, of course, you can scatter this light out of sight, and then again, from this ray, along this direction, then, energy is removed. Light can also be scattered into the ray, of course, and then it's added, right? Okay? So we'll come to those and how they interact throughout these bundles of ray with the light, and to describe them, we need to know how they absorb, how they emit, how they scatter, and how light is transported throughout this ray. That's the topic for chapter 3 and so forth. Now, though, we will start by trying to define this specific intensity, and I will here follow my colleague, John Castor, who set up the following neat experiment, or a thought experiment that we can use to define this. Say that we have a nice apparatus here, yeah, which has a little shutter here, which we can open and close at will. Yeah? And then we have, here we can have a bunch of material which all emits light. Now on this side, on the right-hand side, we evacuate and we have a pure vacuum. Okay? And then we have it closed, and then we open it and we let through light from the source here. Say we had a light bulb here or whatever, right? Yeah? And then we let it shine through this little shutter here. Okay? And then we have a collector at some distance, yeah, say over here, with some area, call it A2. And then that will collect a certain amount of energy, right? Yeah. So now we will open the shutter here for just a proportion, a time delta t. So we can easily imagine that the amount of energy we will receive here will be dependent, or in this case proportional to delta t. Okay? We further say that it's a smart shutter. If I try this just like, you know, I put up a hole like this, then I don't have any bandwidth, right? I will just let through all frequencies, but this apparatus is more clever than that, so it only lets through within a bandwidth delta nu, where nu is the frequency of the light. So within a small bandwidth here, say within a small interval of frequencies, light is let through. The rest we don't let through. A smart shutter. Yeah? And then of course this will be proportional to delta nu as well, we can imagine. And this shutter, we make it very small, but it still has some sort of area, right? A1. The bigger we do that area, the more light will be let through, so we will have an area 1 here. Okay. And then we shine through light. And we collect it there. So obviously, the bigger we do this, the more light we will collect. it spreads out like we have discussed already. So we will have a proportionality constant A2 there as well. But then we have this inverse square law, the fact that the light spreads out like your light bulb. Think about the light bulb in your living room when you're reading a book. Can't go too far away. So the further away we put this, we put that at the distance r, the less light we will collect because it spreads out more and more. Yeah? And that's inversely proportional then to the radius squared, as we know. Okay. And then we can actually define the specific intensity as the proportionality constant in between here. Can define the specific intensity, I nu. I will come to the subscript later as this. Okay? So, just putting this, it's just the amount of energy collected in a time delta t in a bandwidth delta nu, an area A1, and within a solid angle delta omega. Whereas you can see my solid angle here now is just A2 divided by r squared. Okay. And that we can use as a basic definition of the specific intensity quantity. Now, the solid angle here will come back throughout the course a lot of times, also when we do a lot of calculations in the beginning of the class. So we will think about it a little bit more. Huh? Now, generally, you can think about it as a 2D angle. What do I mean by this? Well, we can have an 1D angle, right? Call it theta, okay? We have r there, and we have a little here, and then in the small angle approximation, you know that theta r is big R. Yeah? This we know from physics A. And then you can have a 2D angle, of course, which is the extension then, that, so, like so. Terrible drawing. There will be a lot of terrible drawings during this class. Just get used to it, I almost said. Here, you have like a delta omega, 2D angle, you have a distance r, and you have an area there. So in the same way then delta omega, or just omega, r squared equals to a. That is then your solid angle. Okay? The two-dimensional equivalent. Now, we will also use quite often more formal, strict definition of this solid angle, which you can then also look from setting up your coordinate system, x, y, z, okay? And then you put up your angles here. So we're going to draw a little bit of a little area here again. Like so. We have an area there. We have some theta angle there. We project it down. And we have our phi angle there. Okay? If we call this now a differential area dA, then by using our standard methods, we know that dA in this case is r squared sine theta d theta d phi, or r squared d omega, where the omega then is the solid angle, which is sine theta d theta d phi. Okay? By extension, you can see that, okay, if I just want to take the integral over the solid angle, that means taking the integral over the full sky here. We skip the distance, so we skip the r squared. Yeah? And then we can just solve this integral, which is then just theta from 0 to pi, phi from 0 to 2 pi, sine theta d theta d phi. And this, if you try it out, do it, should come out as 4 pi. If it doesn't, I made a mistake and you will correct me later. There often I do some algebraic mistakes on the blackboard, then say it immediately. It's the best way of getting it done, and then we'll sort it out if we can. Okay? Together. I'm very difficult to offend in that place. Let's just say it like that. So just say it out loud. You forgot the delta E there. You did that and so forth. It's a good way of also thinking of when you're taking your own notes. Huh? So that's the solid angle, and we will use it quite a lot when we work with the specific intensity and its various related physical quantities. Now, one note here about the quantity of specific intensity, and that is I sort of need to make about the units. Okay? We can see here that I nu has units of energy, right? Per unit time, frequency, area, and solid angle, which you will often see in the lovely units of ergs, per second, per hertz, per centimeter squared, per steradians. So what is going on here? Well, that's because I'm an astronomer, and we astronomer, because of tradition, I suppose, nowadays, we often use what we call the CDS system. CDS stands for centimeter, gram, seconds, okay? Now, I mention this here because when I do my examples during a class, for example, when I did the densities of the universe versus that of the air in this room in the beginning of the class today, you might have recognized that I talked about grams per cubic centimeters. I didn't talk about kilograms per cubic meters. And that's because we often use these CDS units instead of the standard SI units. Now, if you want to do SI units in all your exercises and also exam, that's completely fine by me. Huh? But you have to be aware of the translations. And when you read, for example, the course book, when I do my examples, when we do the calculations, I very much often use the CDS units. Again, I'm an astronomer. What can I say? Sorry for this. There is a simple translation, though. You can use this CDS, centimeter, gram, second, to almost always get there. So I will just take one example, right? So ergs, that's energy, okay? Energy in SI is joules, yes? So what do we have energy? Well, the easiest for me to think about energy is like the kinetic energy. It's something like mv squared, right? mv squared over 2. So actually, a joule is mv squared over 2. So that's kilograms, mv squared. That's meters squared per second squared, right? Yes? So that would be then 10 to the 3 grams, and then 10 to the 2 centimeters squared, seconds squared. So we have 10 to the 7 grams, centimeters squared per second squared, which is then 10 to the 7 ergs. So that's how you can do the translation, right? That's just a unit conversion thing. Okay. That's just a note on the CDS units, which, well, that is how it is. Okay. Now we have our specific intensity. We have talked a little bit about the solid angle, introduced it. You need to do some calculations on that in order to get used to it, I would say. There are a lot of exercises for you available. And we introduced our lovely CDS systems. Okay. Okay, so we're going to start with lecture number 2 in radiative processes in astronomy. So last time we had our first class and we sort of set the stage a little bit, talking generally about electromagnetic radiation as our main source of information from cosmic objects. Actually, for most of the time, it's been the only source. We have gravitational waves now, very excited. But that's not what we're going to talk about in this course, of course. The primary source remains the light. We talked a little bit about what that is and what perhaps differs doing experiments in astronomy and astrophysics as compared to other fields of physics where we can easily, sometimes not so easily, set up experiments here in the room, in a lab, and get out the results. We can look at pens that fall to the ground, etc. That we cannot do with the cosmic objects, of course. What we can study is the light that we receive from distant galaxies, from distant stars, from our sun, from the universe as a whole, all of which we will talk about during our course. We also talked about we will use different descriptions of light. We have the classical picture of light as electromagnetic radiation. That will be useful for us during parts of the course when we look at, for example, scattering as a classically damped harmonic oscillator. We will often refer to light as photons, particles of light that carries energy, proportional to their frequency, or inversely proportional to the wavelength, as we already learned on Wednesday. They also carry momentum, which is essentially their energy divided by the speed of light c, which is the constant that photons travel with through vacuum. Now, we do start our course, however, with a detailed description of what we call what I call a macroscopic description of light, where we view bundles of light or rays of light traveling then in straight lines throughout space in the absence of interactions with matter. Those interactions of matter are, of course, critical, and we will discuss them in much more detail, in particular in the next chapter and throughout the rest of the course. It leads us to the topic of transport of radiation or radiative transfer, which is something we concern ourselves very much with in astrophysics when we analyze observations of light from cosmic objects. It is, in some sense, I guess, similar to the geometric optics limit that you might have encountered in other physics courses. And that is the topic now, where we are. We're in chapter 2 in our course book, where we already defined the main quantity that we use, the basic quantity that we use to describe light in this macroscopic description. The specific intensity, I knew, which was the energy per unit time, per unit frequency in a small frequency bandwidth, per unit area, and per solid angle. Okay? Subscript nu here just means that we're taking it at a specific frequency, at a specific photon energy, or more correctly, in a small bandwidth. Yeah? And this with a small bandwidth is important because when we later will discuss properties of the specific intensity in various contexts, then we have to always keep in mind that the quantity that is preserved is actually I nu times d nu, where d nu now is just the equivalent differential, equals I lambda d lambda. That is, you cannot just take an expression for I nu and then plug in and get the equivalent for a lambda. You have to consider the bandwidth here. Yeah? Now, that can always, of course, be easily calculated because we have C equals nu times lambda as our basic definition, right? So to actually calculate the derivative, I even leave it for yourself. You can see it in the course book, of course, right? Particularly, this can cause some confusion. Well, it's not confusion, but it's important to keep in mind when we, for example, in the next chapter also discuss black body radiation, equilibrium radiation. And we look at different curves of that, the so-called Planck curves. Yeah. So we also introduced that, okay, sometimes it is useful for us and also for notational simplicity to work with frequency integrated quantities. Just can call it the intensity then, and then it's just the specific intensity integrated then over all possible frequencies, okay? From this, we used this to also then define the energy density of radiation, okay, which was 1 over C integral over all solid angles, integral over all frequencies of I nu d nu d omega. We will later relate that also to the various angular moments of the specific intensity. So sometimes in literature and also in these notes, you will refer to what is called the mean intensity. And the mean intensity, that is just the specific intensity averaged from all directions. And you can see just by this, averaged by all direction means integration over all solid angles, the four